This video we are going to study about the imperfections in solids or defects in solids. Now we know that a solid consists of large number of small crystals. Even these crystals have defects in them. So what do you mean by the term imperfections in solid? They are the defects or the imperfections are irregularities in the arrangement of constituent particles. So if there is any change in the arrangement of constituent particles, we say that there is a defect or it's an imperfect solid. So imperfections or defects in solids means irregularities in the arrangement of constituent particles. Now mainly there are two types of defects. So imperfections in solids are mainly classified into two types. The first type is called point defect, and the second type is line defect. Now, what do you mean by point defect? Point defects are the irregularities or deviations from ideal arrangement around a point or an atom in a crystalline substance. So if there is an irregularity in the arrangement of atom in a crystalline substance, we call that defect as point defects. Because we know when we discussed about the space lattice unit cell, we considered these constituent particles as points. So if there is an irregularity in the arrangement of points, we call that defect as point defect. Now, what do you mean by line defect? Line defects are the irregularities or deviations from ideal arrangement in entire row of lattice points. So, if you take one row of atoms or constituent particles, if there is any irregularity in the entire row of the lattice point, we call that defect as line defect. Now, we will confine our study only to point defects. We are not studying about line defects in solid state. So let us study in detail about point defects. So, point defects. Now, point defects means irregularity in the arrangement or irregularity around the atom or a point. Now, these point defects are classified into three types. First is stoichiometric defect, second is impurity defect, and third is non-stoichiometric defect. So let's study about the three types of point defects. First one is stoichiometric defect. Now, what do you mean by stoichiometric compounds? Stoichiometric compounds means compounds in which the number of positive and negative ions are exactly in the ratio as indicated by their chemical formulae. Okay, so the number of positive and negative ions will be in the same ratio as indicated in their chemical formulae. They are called stoichiometric compounds. Now, what do you mean by stoichiometric defect? Stoichiometric defects are point defects that do not disturb the stoichiometry of the compound. So, in stoichiometric defect, the stoichiometry of the compound means the number of positive and negative ions, that ratio will not change. It will not affect or disturb the stoichiometry of the compound. Now, the stoichiometric defects are also called intrinsic defect. Intrinsic defect, or they are also called thermodynamic defects. Now, again, stoichiometric defects can be classified into two types. They are vacancy defect and interstitial defects. So, next is classification of stoichiometric compounds into two types. The first one is called vacancy defect. Now, what do you mean by vacancy defect? From the name itself, something is vacant, something is missing out. So, vacancy defect means when some of the lattice sites are vacant, the crystal is said to have vacancy defect. Now, if we draw a diagram for vacancy defect, we can say these are the spheres or atoms or constituent particles. If some of the lattice points are vacant, suppose this is vacant, we can say that there is vacancy defect in this crystal. Okay, and you know that since some constituent particles are missing, we can say that it will result in the decrease in density of the crystal. And this defect can also develop when you heat a substance. So that is vacancy defect. Now the second type of stoichiometric defect is interstitial defect. So B is interstitial defect. Now, interstitial defect means when some constituent particles occupy an interstitial site, the crystal is said to have interstitial defect. And this interstitial defect will increase the density of the substance. So, if you are to draw the interstitial defect, we can show it like this. These are the constituent particles. Now, interstitial defect means some constituent particles occupy interstitial sites. So, these are the interstitial sites. So, if there are constituent particles in the interstitial sites, we call this defect as interstitial defect. And you know, as the number of particles is more, the density increases. Okay. Now, this vacancy defect and interstitial defects are usually exhibited by non-ionic solids. But for ionic solids, we have two other defects, that is called Frenkel and Schottky defect. So, next we are going to study for ionic solids. Ionic solids, the defects are Frenkel and Schottky defect. So, first let us see what is Frenkel defect. Now, all these comes under the stoichiometric defect. So, Frenkel defect and Schottky defect. What is Frenkel defect? Okay. Now, Frenkel defect is shown by ionic solids. And what is Frenkel defect? In Frenkel defect, and I told you, ionic solid means it will have cation and anion. Now, in Frenkel defect, the smaller ion, which is the smaller ion, the cation, is dislocated from its normal site and it moves to an interstitial site. So, if we draw the Frenkel defect, you can see it's found in ionic solid means we have plus, minus, plus, minus. Suppose this is an ionic solid. What do you mean by Frenkel defect? Dislocation of a cation from its normal site. So, suppose I am going to dislocate this cation from its normal size means it will move from this side, means what is created there? A vacancy is created here. Now, where will it go? It will be in the interstitial site. So, you can find it somewhere here. Okay, so you can see that this is Frenkel defect. Now, here you can see a vacancy defect is created as its original vacancy defect is created at its original site and an interstitial defect is created at its new location. So, this is Frenkel defect, that is a cation will get dislocated from its original position and it will occupy an interstitial site, and this is found in ionic solids. Now, Frenkel defect will it cause any change in the density of the solid? Because nothing is going out. We have the same number of cations and anions, which means there is no change in the density of the solid in Frenkel defect. Now, this Frenkel defects can also be called as dislocation defect. So, Frenkel defect or dislocation defects. Okay. Now, which type of ionic compounds show this type of defect? Now, Frenkel defect is observed if there is a large difference in size between the ions, that is between the cation and anion. For example for compounds that show Frenkel defect is zinc sulfide, silver chloride, silver bromide, silver iodide. Now these compounds, there is a large difference between the cation and anion size. Okay, now there is something that you have to note. The alkali metal halides, for example sodium chloride, then potassium chloride, they will not show Frenkel defect. Why? Because you know that the alkali metals in the periodic table, alkali metals have the largest size. So the cation will also be of large size. So the cation cannot dislocate. Even if it dislocates from its original position, it cannot fit in the interstitial site because of its bigger size. So alkali metal ions will not show Frenkel defect. So tell me about Frenkel defect. Frenkel defect, in Frenkel defect, the cation is dislocated from its original position and it occupies an interstitial site. Frenkel defect does not cause any change in the density of solid, and in Frenkel defect is observed when the difference between the ion, size of ions is very large, and study examples for compounds that show Frenkel defect. Now the next type of interstitial defect is Schottky defect, or the type of stoichiometric defect that you find in ionic solids is Schottky defect. Now what do you mean by Schottky defect? Schottky defect means the number of missing cations and anions, or some cations and anions are missing from the lattice site, and the number of missing cations and anions are equal in order to maintain electrical neutrality. So I am going to show the Schottky defect. Again we have minus, less. Now some cations, equal number of cations and anions are missing. So if one plus ion is missing, one minus ion will miss. Again, if one more minus ion is missing, one plus ion will miss. So this is Schottky defect. Now you can see that in Schottky defect, what happens to the density of the solid? Density of the solid decreases because there is missing of anions and cations. Now this defect is found in ionic compounds where the size difference between the cation and anion are almost same, or if the size of the anion and cation is almost similar, then such compounds will show Schottky defect. Now examples for compounds that show Schottky defect is sodium chloride, potassium chloride, cesium chloride, etc. Now there is a very important point to be noted, that is silver bromide. This is a compound that shows both Frenkel and Schottky defects. Okay, so this is asked as a question. Name a compound that show both Schottky and Frenkel defect. The compound is silver bromide. So this is about Schottky defect. So what is Schottky defect? Schottky defect, there is equal missing of cations and anions to maintain electrical neutrality. The density of the solid decreases, and this type of defect is found in ionic compounds where the size of cation and anion are almost similar. So this is about the stoichiometric defects, where the stoichiometry of the compound or the solid is not disturbed. There is no change in the formula or the ratio of anions and cations. Now next type of point defect. The second type of point defect is impurity defect. Impurity defect. Now for this, let's take an example. We have a sodium chloride crystal. So in sodium chloride crystal we have sodium ions and chloride ions. So Na plus, Cl minus, Na plus, Cl minus. Then now to this sodium chloride crystal I am going to add an impurity, and the impurity added is strontium chloride. Now you know strontium chloride, the charge of strontium ion is Sr2+. So what happens when I add strontium ion? It will replace sodium ion in the sodium chloride crystal. Now, how many sodium ions will be replaced? 2 sodium ions will be replaced by 1 Sr2+ ion. So, to maintain that electrical neutrality, we have to replace 2 Na+ with 1 Sr2+. Okay, so I am going to remove 1 sodium ion and 1 more sodium ion, and with what I am going to replace it? I am going to replace it with Sr2+ ion. So you can see here a vacancy, one lattice site is vacant. There is a vacancy defect also here. Okay, now the electrical neutrality is maintained. Now this is what is called impurity defect, and you can see which ion is, which vacancy is created here. A cationic vacancy is created because one cation, that vacancy is there, it's missing. Okay, so cationic vacancy is created. Now there is another example for this impurity defect. Another example is that is cadmium chloride and silver chloride. So here you can see silver chloride has Ag+, Cl-. Suppose it is a silver chloride crystal. To that we are adding the impurity as cadmium chloride. Cadmium chloride, cadmium has 2+. Each one cadmium ion will replace 2 Ag+ ions. Okay, so that is the impurity defect. Now the last type of point defect is non-stoichiometric defects. So number 3 is non-stoichiometric defect. Now, non-stoichiometric defects means in this type of defects, the stoichiometry of the compound will be affected. Means there will be a change in the ratio of positive and negative ions in the formula of the compound. So that is non-stoichiometric defects. Okay. Now, these defects are divided into 2 types. First is metal excess defect and second is metal deficiency defect. So, metal excess defect means the amount or the ratio of that cation present. It is the metal is cation. Cation present will be more. And metal deficiency means the amount of that metal ion will be less. So, they are non-stoichiometric compounds now. So, first let us see non-stoichiometric defects. The first type is metal excess defect. Metal excess defect. Now, again this metal excess defect can be classified into 2. One is metal excess defect due to anion vacancy. So, first we are going to see metal excess defect due to anion vacancy. Now, this defect is very, very important. Here we have a question. Why sodium chloride crystals are yellow in color? Or why lithium chloride is pink in color? Or why potassium chloride is violet or lilac in color? When you heat these salts, you observe for sodium chloride yellow color, lithium chloride pink color, potassium chloride violet color. Now the reason is based on what? The metal excess defect due to anion vacancy. So let's study about the yellow color of sodium chloride. How this sodium chloride when heated show yellow color. Now so these are the examples for the compounds that show metal excess defect due to anion vacancy. Now let us discuss how sodium chloride crystals get yellow color when heated. Now when you heat crystals of sodium chloride in an atmosphere of sodium vapor, what happens? The sodium atoms are deposited on the crystal. Now, what we have in the crystal lattice, we have sodium chloride. We are heating sodium chloride in sodium vapor. So, sodium chloride means we have minus, plus, minus, plus. Minus represents chloride ion and plus represents sodium ion. Plus, minus, minus, plus. Okay. Now, this is sodium chloride crystal. I am heating this in presence of sodium vapors. So, what happens, or in an atmosphere of sodium vapor, what happens? The sodium atoms are deposited on the surface of crystals. So, when you heat this in presence of sodium vapors, sodium atoms will be there on the surface of crystal. Now, what will happen from the sodium chloride crystal? The chloride ion Cl- will come to the surface because there is more number of sodium atoms on the surface, sodium atom. Now, when this chloride ion Cl- come from the crystal to the surface, what will sodium atom on the surface do? They will lose electrons and sodium will change into Na+, and that Na+ will combine with Cl- to form sodium chloride. So, what will happen? You can see that there will be a anion vacancy created. That is, one anion Cl- will be removed. Now, who will occupy that position? We know that the sodium atom at the surface, they lost electron and changed into Na+. So, that electron lost by sodium atom at the surface will diffuse into the crystal and they will occupy this anion vacancy. Okay, and the electron entrapped in this anion vacancy, it is unpaired electron and we call this as F centers. So, you can see here we have now metal in excess amount, that is sodium metal is there in excess and there is an anion vacancy, and here the anion vacancy is occupied by the electron and we call that as F centers. Now, what are F centers? They are the anionic sites occupied by the unpaired electrons. They are called F centers, and these F centers are responsible for the color. Now, how are they responsible for the color? When you heat the sodium chloride crystal, now what happens? The electrons entrapped in F centers will absorb energy from the visible light falling on the crystal and these electrons will get excited. Okay, and we see that as yellow color. Same way we can observe a violet color when you heat potassium chloride and a pink color when you heat lithium chloride crystals. So, this is very important. The color of sodium chloride or lithium chloride or potassium chloride is due to the formation of F centers. F center means the anionic sites which are occupied by unpaired electrons, and these electrons are responsible for color of the crystal. Now, the second type of non-stoichiometric defect, again we have two types, one is metal excess defect and second is metal deficiency defect. We are discussing metal excess defect. Metal excess defect is again of two types. The first one is metal excess defect due to anion vacancy. Now, we will discuss the second type of metal excess defect. The second type of metal excess defect is, metal excess defect due to presence of extra cations. At interstitial sites. So, second type of metal excess defect is metal excess defect due to presence of extra cations at interstitial site. Now, here also we have a very important question. Zinc oxide is colorless, but it turns yellow on heating. What is the reason? The reason is based on this. That is metal excess defect due to the presence of extra cation. Which is the cation in zinc oxide? Zinc ion at interstitial sites, means at the vacant sites. Now, what happens when you heat zinc oxide? What is the reaction taking place? This is the equation. On heating zinc oxide, heat, you get Zn2 plus half O2, oxygen gas, plus 2 electrons. Okay, so now zinc oxide on heating, it loses 2 electrons and it loses oxygen and it turns yellow. Now, if we show it, I am going to show it as a structure, N plus X minus. M plus represents zinc ion and X minus is oxide ion. Instead of plus minus, I just wrote M plus and X minus. X minus. Now, what happens? You can see that the zinc ion Zn2 plus is produced on heating zinc oxide. Oxygen gas will escape out and Zn2 plus ion will occupy the interstitial site. So, you can see, suppose this is the structure of zinc oxide. What happens? Zn2 plus occupies the interstitial site and electron will occupy the neighboring interstitial site. So, you can see electron somewhere here. Okay, now you can say that the conductivity of this zinc oxide is very high because of the presence of this electron. So, this is about zinc oxide crystal. Zinc oxide is colorless, but it turns yellow on heating because of excess of Zn2 plus ions in the interstitial site and electrons occupying the neighboring interstitial site. Now, since there is excess of Zn2 plus, now the ratio of zinc to oxygen in the compound zinc oxide, the actual ratio is 1:1. Now, you can say that the ratio will not be 1:1 because there is excess of metal ion, zinc ion. So, what will be the ratio? It will be Zn 1 plus X O. So, you can say that this is a non-stoichiometric compound. Okay, because there is excess of metal ion in this. So, this is metal excess defect due to the presence of extra cation at the interstitial site. Now, the last type of defect, that is the second type of non-stoichiometric defect, is metal deficiency defect. So, in these two cases, we had metal excess defect. Now, the last one is metal deficiency defect. Metal deficiency defect. Now, this type of defect is mainly exhibited by transition metals, even metal excess defect also, because transition metals are compounds which can show variable valency. So, metal deficiency defect is exhibited by transition metals. Okay. Now, example for metal deficiency defect is FeO, iron oxide. Now, here comes a question, why is FeO not formed in stoichiometric composition? Why FeO is not formed in stoichiometric composition, which means that FeO is a non-stoichiometric compound and it is metal deficiency defect. Now, this FeO, actually the composition is, actual composition is 1:1, the ratio, but since it is metal deficiency, the composition of FeO is Fe 0.950. This is the actual composition, or we can say the composition lies in the range of Fe 0.930 to Fe 0.960. So, the actual composition is 0.950, but we say that it ranges, it varies in this range, 0.93 to 0.95, which means that FeO means ion is in +2 oxidation state. There is a missing of Fe2 plus ions in the crystal lattice of FeO, and here the Fe2 plus cations are missing, and the loss of that positive charge is made up by the presence of required number of Fe3 plus ions. So we have Fe2 plus ions missing, but that charge is maintained by adding an ion of higher charge, that is Fe3 plus. So this is about the non-stoichiometric defect, in which there is a metal deficiency defect. Again, when you add Fe3 plus ion also, so there will be a vacancy of Fe2 plus ion, which means the deficiency of Fe2 plus. So this is metal deficiency defect. Now with this we complete the imperfections or defects in solids. Thank you.